All right, so welcome everyone. It's really a great pleasure today to have Wenting Zhang here today with us, so virtually at least. So Wenting is a PhD student currently at UC Berkeley, and she's co-advised by Jon Stoica and Luca Rapopa. And actually, prior to that, she studied at MIT, where among many people she worked with Barbara Liskov. So our work is at the intersection of systems, security, and cryptography. And so the very exciting component here is that a lot of our work takes cryptography, which so far has been mostly within the realm of theory, and then builds systems out of it and tackles a lot of challenges in doing that. Okay, and that's going to be also the main part of our talk, which is going to talk about tools for systems for secure collaborative computation. So just a reminder before I leave the stage to Wenting. So if you want to ask any questions, so try to keep big questions for the end, just ask clarifying questions during the talk. And if you want to do so, just communicate the intention to ask the question in the chat, and then I will just I will interrupt kindly Wenting and just give you a chance to speak. Okay, and with that, I'll just leave the stage to Wenting.
Okay, great. Yeah, so thank you for the wonderful introduction, and I'm very happy to be here virtually from Berkeley. And today I'm excited to share with you some of the work that I did while being a grad student here on building systems that enable secure collaborative computation by allowing multiple parties to share their data with each other for computation, but without showing their data to each other in plain text. And really, the need for collaborative computation stems from the fact that organizations today are increasingly using advanced analytics techniques to extract a tremendous amount of value out of their collected data. And while there has been a lot of work on improving these analytics techniques, organizations still face a pretty fundamental problem in data acquisition, in that acquiring high quality data can be actually rather difficult. And in many domains, such as finance and healthcare, applications often require data that reside across multiple organizations. And so really what we're seeing today is that there's a fundamental tension between the fact that applications need high quality data, large amount of high quality data, and the fact that organizations own sensitive data that cannot be shared with each other. So, and I'm going to actually illustrate this tension, right, by showing you two real world use cases that we have encountered. So the first use case is a financial use case. So here we have a bank that wants to use analytics and machine learning for detecting money laundering activities. And by the definition of money laundering, what happens is that criminals try to conceal their illegal activities by laundering money across many banks. And so in order to compute an accurate result for detecting these illegal activities, one would ideally compute on customer transaction data that's collected from multiple banks, right? But currently this cannot be done because the banks are competing with each other and they're not willing to share their plain text customer transaction data with each other. And here I'm actually showing you a quote from the Chief Risk Officer of Scotiabank, who said that collaboration will be very vital for the future of anti-money laundering and will enhance yields by orders of magnitude. And I'll come back to this a little bit later, but we're actually working with Scotiabank on this anti-money laundering use case. The second use case is a flu outbreak prediction use case, which is somewhat relevant today. So in this previous use case though, so there are annual flu outbreaks in California that happen in California. And here we have a medical organization that wants to predict the locations of these outbreaks before they happen so that vaccines can be distributed more effectively. Right? So what happens right here is that in order to compute something like a flu outbreak prediction model, one would ideally use patient data that's collected from multiple hospitals across California, right? But again, this currently cannot be done because these hospitals cannot share the sensitive plain text patient data with each other due to policy regulation. So as you can see, there are many applications that can be enabled by data sharing. I only shared two with you, but simply cannot happen today because the data in question is quite sensitive. So how can we solve this, this problem, right? So one possible solution is simply to leverage a trusted third party that computes the result by basically getting off the party's plain text data, right? But from talking to our industry collaborators, they felt like this is not a great solution because it is one extra party that you have to trust, right? They're worried about cost because paying for a trusted third party can be very expensive. And from the trust third parties, from this possible third parties perspective, right? We have talked to some of them as well, and they were actually very concerned about liability issues. Because if it's collecting all this sensitive data from all these banks or hospitals, it becomes a high-value central target for attacks, right? So my graduate research has focused on solving this problem, this collaborative computation problem, by building systems that enable this kind of computation without utilizing a trusted third party that sees all of the plain text data. And the key guarantee that my systems provide is that the participants can actually share their data with each other for computation, but then without showing this data in the plain text to each other. And in fact, the parties only learn the final result of the computation without ever seeing the input or the intermediate results. Right. So how do I do this, right? So my approach, right? In terms of my approach, I am a systems builder who builds secure systems by leveraging advanced cryptography, and achieve this via a careful co-design of systems and crypto. And really, by bridging the gap between these two areas, my systems are able to provide strong and provable security guarantees and are actually often orders of magnitude faster than the more straightforward approaches combining these two areas together or the prior work in this area. So therefore, right, the work that I did during my graduate career were mainly at the intersection of these two areas, where I utilized a wide range of tools from both areas and also innovated on them to produce a practical and secure solution. And in this talk, I'm actually going to focus on two of my works that secure two different workloads. So the first is Opaque, which secures SQL analytics. And another work is called Helen, which secures machine learning training for regularized linear models. So it's two different workloads that are commonly seen in this collaborative computation setting. And in terms of the approaches that people usually take for solving this problem, right, there are two major approaches. And the first approach is something called secure multi-party computation, or MPC for short, which allows parties to run collaborative computation in a just completely decentralized manner using only cryptography. And the second major approach is via doing this kind of computation via the use of hardware enclaves, which are these hardware-based mechanism for secure computation. And I'm going to first focus on Helen, which uses the first approach, and we'll come back to Opaque after Helen's done. So secure multi-party computation, right, or MPC. So what MPC is a type of a cryptographic protocol, right, that allows parties to emulate a trusted third party, but without having access to an actual physical trusted third party. And in fact, what the parties do is that they emulate this trusted third party by only doing local encrypted computation, as well as sending encrypted messages to each other. And in fact, the security guarantees of utilizing an ideal trusted third party are also preserved in that no party should learn any party's input beyond what is learned from the final result of the computation, right? So very strong security guarantees. But in terms of the setup, right, so our bank is pretty excited to utilize MPC to do their computation, but it wants to make sure that its desired secure properties are all satisfied. Right, so sure, we're in this ideal trusted third-party model, but the bank first of all wants to make sure that the protocol should be secure even if all the other banks colluded with each other. So you have one honest bank in this diagram, you have one honest bank at the top, and then two that are compromised by the same adversary on the bottom. So this is what we call a dishonest majority setting, right? So if you have P parties and P minus one, out of them can be compromised by the same adversary. And second, our honest bank wants to make sure that the protocol should be secure, even if the adversary can deviate from the protocol. So for example, right, this yellow bank here, it might deviate from the protocol by doing some incorrect encrypted local computation by substituting different inputs into the system, inconsistent inputs into the system, or send incorrect encrypted messages to the honest party, right? And this is what we call malicious security. So we assume that we want to protect against a malicious adversary. So if we take a look at the prior work, right, there's a lot of prior work in this area. Pretty much all of them do not fulfill the previous two requirements. So first of all, many of them actually only support two parties. So they are not generalizable to the multi-party setting. And they also additionally assume that the adversary who compromises a subset of the parties is actually what we call honest but curious. Namely that the adversary does not try to deviate from the protocol at all and is instead more of a passive eavesdropper, right? So if we take into account both of these important properties that I mentioned before, as you can see on the bottom here, right, the framework that supports, or the kinds of framework that supports these two important properties is a more generic, maliciously secure MPC system like SPEEDS, right? So we can technically compute even regularized linear model training in more generic MPC, but of course the challenge is that it's rather expensive due to both expensive compute, expensive communication. So it's often sending a large amount of bytes or many round trip. It has many round trips as well, and also every party needs to participate in the entire computation, right? So if you have any kind of pre-computation or local computation, then because it's this maliciously secured dominant majority setting, everybody still has to participate, right? So what does this translate to more concretely, right? So in fact, if you take a more pretty commonly used plain text training algorithm like a stochastic gradient descent or SGD, and you want to train, let's say, a type of regularized linear model like Lasso, using SPEEDS, a generic maliciously secure MPC framework, and for 4 parties, 100,000 samples per party, and data set that has 90 features, we estimated that it would take 3 months to train this model. Actually, we couldn't even run it because the frameworks actually run out of memory very early on. So the question we want to ask is, can we actually design a more efficient protocol just for regularized linear models, right? So we're not trying to handle, a generic functionality. And so Helen is our solution to the previously proposed problem, and we decided to focus on regularized linear models because it actually has many applications in the real world, including the healthcare application I mentioned before. And here I just want to clear things up a little bit about the setup, right? So we are focused in Helen. We're focused on securing the training algorithm according to this MPC definition, right? Which is a setup that is assumed in pretty much all prior MPC literature, which is that what we're trying to do is to emulate an ideal trusted third party, right? So what that means graphically, right, is that we're trying to basically produce this locked box, right? And from the position of the locked box, we similarly assume the following. The first of which is that we actually allow the parties to choose their own inputs, but then once they're chosen, our protocol can ensure that the rest of the training process will always use this input, and the parties cannot substitute some other inputs. And second, we assume that the parties want to compute and release the final result in the plain text to everyone because they're doing this collaborative computation. So ideally, they want to get something out of it, right? As you can see, even in the traditional MPC definition, this is a little bit problematic because it doesn't address things like maliciously chosen user inputs or leaky and undesirable outputs. Right, so this is we assume that this is a bit orthogonal to Helen's system, but I will come back later in the future work section to talk about how to solve these problems from a more systems holistic end-to-end view. Okay, so right, so what is our insight, right? So our insight here is that when running a program, trying to run the program secure, right, inside MPC, just taking the plain text algorithm and putting that in generic MPC will be quite expensive. And what we did in Helen was to create a specialized protocol that enables the cryptographic computation to actually scale independently of the number of training samples. And of course, while still maintaining the same functionality as security guarantees of the original baseline. So what we have here is that for the same problem that I was trying to tackled before, instead of estimate 3 months to train the model, in how long we can actually train the model, right? And actually run it and produce the trained model in less than 3 hours. Right. So how do we get that huge performance boost? So we're really using two main techniques for designing the system. Right. So first, during this co-design of systems, crypto, as well as machine learning, we really have to find alternate formulations of the problem that make the cryptographic computation more scalable, including both reformulation of the data as well as reformulation of the algorithm itself. And second, from starting from these alternative formulations, we designed the cryptographic protocol in such a way that the cryptographic computation is actually split into a single-party plaintext computation, a single-party encrypted computation, as well as the rest of the computation that needs to be jointly executed by everybody. Then we actually push that to a generic MPC. And again, we're able to split the computing in this way by maintaining functionality and security of the system. And so those are the kind of two overviews for our techniques. And now I'm going to tell you a little bit more about more details about how, or a detailed explanation of some of the techniques that we use to enable the system to scale independently the number of training samples. And we'll do so via an example. Right. So before training, what each party needs to do is to gather its training data, and this training data, right, this training input is of size, we assume it's of size n by d, where n is the number of training samples and d is the dimension of data set. And here we're actually additionally assuming, making another assumption here in that n is a lot larger than d. Where you assume that n is maybe in the millions or tens of millions, and d is in tens or hundreds, right? And we found that this is actually a very reasonable assumption for many of the data sets that we looked at. So with this setup in mind, let's take a look at the slow baseline that we started out with, right? Which is putting stochastic gradient descent directly into generic maliciously secure MPC. And doing so is very expensive. And the reason is that it has to, the algorithm, right, has to scan the entire training data set, which means that the cryptographic computation, in this case, right, the MPC computation, needs to take in this very large inputs from all of the parties. And of course, the performance of the cryptographic computation will also depend on, in this case, the number of training samples, which can be very, very big, right? So the first insight that we did, which is right, going back to what I said before, which is alternative formulation of the algorithm. And here, right, instead of using a stochastic gradient descent, we actually identified ADMM, which is an alternative training algorithm that has very nice properties when you're using it, when used for linear models. What happens is that during, when expressed for linear models, it allows this iterative training on a small pre-computed summary. So what happens is that, right, so the parties have this large training data set, and what ADM first does is that it computes a summary of its input data, only locally by each party. And then all of the parties can iteratively train on these summaries. And because the parties iteratively train on summaries of the entire inputs, right, from each party, the algorithm is also able to converge in very few iterations compared to stochastic gradient descent. So with this alternate training formulation, this leads to the following strawman design, right? In that each party can simply pre-compute a summary, since that can be done locally on its own data, right? And then every party can execute the iterative training together, right? On this small data set, on the small summary, using maybe generic MPC. And this is nice because the MPC computation only needs small inputs, right? Now, this is actually would have been fine if we're assuming an honest but curious adversary, but since I previously mentioned that we're actually under the malicious setting, this is a bit tricky, right? Because actually, in fact, the strawman design is only a partial and insecure solution. And why is this the case, right? The problem here is that pre-computation by a single party under this malicious security setting is actually quite tricky. And if we allow a potentially adversarial party to pre-compute a summary, right? Then you could incorrectly compute the summary, for example, by substituting a wrong summary that cannot be mapped to any valid inputs that it could have generated, which will violate this ideal trusted third-party model, right? So basically, intuitively, we're allowing these parties to, we're relying on them to doing something, we're relying on them to do something correctly, but then they could just mess up the computation, right? So, and we want to enforce this ideal trusted third-party model. So of course, one can solve this more naively by simply putting the summary computation inside of generic MPC. But as I mentioned before, right, generic MPC requires every party to participate in a single party's pre-computation. And also the cryptographic computation's cost, as you can see here, will still depend on the number of training samples, right, which is very big. So we never, got rid of that dependency, or rather the dependency is kind of back, right, once we consider this malicious security level. So how do we approach this problem in Helen, right? So we take a kind of two approaches for solving this problem. The first problem we're trying to tackle is this generic MPC scalability problem. So our first insight is to observe that, well, each party can individually pre-compute the summary using its own data. And what we can add in order to enforce that they're doing correctly is simply to make them prove the summary generation using its own data as well. And so instead of using generic MPC, what we did was we actually constructed these specialized zero knowledge proofs, which put it simply is basically a type of a cryptographic primitive that allows a party to prove to another party that certain properties are satisfied, but without revealing certain properties of the computation satisfied, but then without revealing its private inputs, right? And here I'm only showing you the very high level properties because the actual protocol is a bit complex. But for example, one of the gadgets that we use, zero knowledge proof gadgets that we use in our system is a matrix multiplication zero knowledge proof, which allows the prover to prove to the verifier that it holds these encrypted matrices A, B, and C such that A times B is equal to C. What this does is that it offers some integrity properties because the verifier can verify that the computation was done correctly. But at the same time, the prover does not have to reveal the actual plain text contents of A, B, and C, right, to the verifier, and therefore providing nice privacy properties as well. So then, therefore, what we have here is by using these gadgets that we constructed, each party can pre-compute a summary. This way in plain text, and approve the summary computation in zero knowledge using zero proofs, right? So then we're not using generic MPC anymore. So the pre-computation does not have to be executed jointly by every party using MPC, right? But of course, there's still a glaring problem here because the proof is actually quite big, right? So in this case, we're still proving, sure, we're using a different cryptographic primitive, but we're still proving the summary generation using this very large input data set. And so the cost is going to still depend on the number of training samples, right? So that's where our second insight comes in. So our second insight here is that instead of using the original inputs, right, the larger inputs to compute the summary, it's actually possible to find smaller inputs, alternative inputs that can be used to preserve the summary generation, right? So what happens is basically the following, right? So the original inputs can be, you can find reformulated small inputs somehow, right, from the original inputs, and then you can calculate the summary directly from those reformulated small inputs. And then what happens is that the proof is actually reduced to 2 steps. So first, once you found these reformulated smaller inputs, you can directly prove the properties of the smaller inputs to ensure that these smaller inputs can be mapped to some valid original input, right? If this isn't the case, then again, the adversary can substitute some inconsistent wrong inputs here that don't map to any valid original input. And once that is done, right, once you have proof properties about these smaller inputs, then you can go ahead and prove the summary generation from these smaller inputs directly, right? So for the summaries that we have to compute in Helen, we actually discovered that singular value decomposition, or SVD, which is a technique from linear algebra, can actually be used to reveal these alternative smaller formulations of the input data that can still be used to compute and preserve the summary, right? So now, right, instead of putting the entire input data, summary generation from the original input data directly into the proof, what we have is that we first use SVD just in plain text, right, to find these new smaller inputs, and which you can use these new smaller inputs to generate the summary, and then we simply put the proof. What we simply prove, right, two things I mentioned before: properties of these smaller inputs, as well as the summary generation from these smaller inputs. So with this, as you can see, right, the proof will only depend on the size of these smaller inputs, which is always d by d or d by n, or sorry, d by d or d by 1. So the proof computation no longer depends on n, which is the number of training samples, right? So that kind of gives you, that can give you an overview of some of the techniques that we use in designing Helen to kind of remove this dependency on the cryptographic operations dependency on the number of training samples, which really kind of shows you the importance of co-designing systems, cryptography, as well as machine learning, right? And now I will quickly show you some of the evaluation. Unless, yeah, go ahead.
So, a question from the audience, Paul.
Mm-hmm. Yeah, so I have a question. You have these smaller inputs. Why don't you just have the protocol use the smaller inputs in the MPC rather than using the summaries? Couldn't you just replace the summaries with the smaller inputs, the summarized inputs?
Well, I mean, in a way, we are inputting the smaller inputs into this customized MPC protocol, right?
But now you no longer need to prove that the summary was computed from the smaller inputs, because the smaller inputs are already smaller.
Yeah, but then well, I mean, you need to use the summary still, right, during the iterative computation. So are you saying that you can use the summary, input the summary directly without proving properties of the smaller inputs, or prove the summary generation? Because that's not secure, right? Because you can input an arbitrary summary that, again, doesn't map to any possible original valid original input. So you would violate integrity of the computation.
I see. So you'd have to compute, you would be computing the summary from that same size set of inputs as part of the
yeah, exactly. That's necessary. Yeah. Otherwise, you could be kind of computing something arbitrary. Yeah.
I think there's another question.
Okay.
Jennifer?
As maybe like a kind of a question in the same vein, how, like, do we have to also prove that this SVD came from the original data?
Yeah, that's a great question. So here we're actually relying on, it's a little bit subtle. So here we're actually relying on the fact that we allow the parties to choose their own data, right? Because I mean, that's kind of something that, you end up having to allow the parties to do anyway. So what we are proving is that the SVD, the smaller inputs, right, which are basically these smaller inputs, matrices from SVD, we're just proving properties about those to make sure that they can be mapped to some or valid original input. Right, so the honest parties will do that correctly, and the adversary parties, we need to prove this stuff. So we need to prove this because, yeah, otherwise they might input some kind of invalid smaller inputs. Yeah. Okay. Okay.
Yeah, no more questions.
All right. Okay, I'll move on. I'm sorry, it's a little bit hot because I'm under the sun here. Okay, so I'll jump into the evaluation of the system then. So in terms of the experiment setup, we ran the experiments, we benchmarked on 4 parties. EC2, 2 are located in Oregon, and 2 are located in Northern Virginia to kind of emulate this wide area network setting. The baseline that we compare to is this SGD implemented in SPIECE, which is this generic maliciously secure MPC platform. And SGD, we decided to use that as a baseline also because it's using some of the prior work in secure learning as well. And in terms of the training assumptions, we're assuming a couple of things, right? So we're assuming that SGD has to scan off the data. This is because also, you might have, for example, rare features in data sets that don't occur very often. So we assume that you need to at least scan off the data once. And for ADMM, right, because we use a different training algorithm, we actually experimentally found the maximum number of iterations that we need to converge using some different data sets from UCI. And this is because Helen uses a different training algorithm, right, that alternative formulation that iterates over summaries of the entire data sets instead of scanning kind of the data set directly. So in terms of the evaluation here, I'm showing you just one graph. We have more graphs in the paper, but on the x-axis here, I'm scaling the number of samples of Hardy. And on the y-axis, I have the time. And blue line here is the estimate secure baseline, right? So as you can see, it scales linearly. As you increase the number of samples per party because SGD simply has to scan more data, right? And you're putting off that instead of MPC. Whereas Helen, right? This is Helen's performance, the green line. It looks constant, but it actually does scale up very slowly. The reason is that, right, we split this computation into plain text computation and cryptographic computation. And the cryptographic operation, we made it so that it does not have to depend on the number of training samples. And therefore, and since the cryptographic operation greatly dominates the plain text operation, as you can see, you basically see this linear constant behavior. And so for 100,000 samples, we see about a 900x performance scale. Right, and that's it for Helen. And if we don't have any more questions, I'll move on to Opaque, and I can answer more questions at the end, of course. Okay. Okay, so now switching to a pretty different type of system, which is Opaque, secures SQL analytics using hardware enclaves, so pretty different approach. So what are hardware enclaves, right? You might have heard of them before, but they're basically hardware enforced secure execution environments that allow you to run your code securely, even in the presence of a malicious operating system, right? So what these enclaves have is encrypted enclave memory, which is very nice because this allows you to keep secret data inside these enclave environments. And also remote attestation, which is a way to allow a client to make sure that the correct piece of code has been loaded into these enclaves so that you are not, running some malicious piece of software. That would be kind of bad, right? Because it's reading your secret data. So compared to Helen, right, for the enclave approach, we decided to introduce a third party into the picture, but not a trusted third party, because many organizations are already outsourcing their data to the cloud, but are still increasingly concerned about the cloud having access to their plain text sensitive data. And as it turns out, in response, what many cloud companies have been doing is they have been introducing bare metal instances and/or services that support this hardware enclave usage, right? So this is very nice because having hardware enclave support in the cloud means that this kind of platform becomes a very viable approach for collaborative computation. And if you can support a platform that can enable this kind of computation that runs inside enclaves, then basically each party can simply encrypt its data, send it the encrypted data to the cloud, and the enclave, the platform that's running, software platform that's running inside the enclaves can read the encrypted data and then operate on it, decrypt inside the enclave, of course, and operate on it. And of course, using the cloud is also nice because it gives the parties easier access to this hardware and also still take advantage of the elastic compute resources offered by the cloud. So is this easy? You just put some software inside hardware enclaves. The problem is not super simple because these hardware enclaves are also prone to an important type of attack vector called data access pattern leakage, where the adversary can actually learn information about the encrypted data only based on observing, for example, the sequence of memory addresses are accessed, or I guess network communication patterns, such as which machine is sending information to which other machine and how many bytes, right? So it's a bit abstract, and I will show you an example of such an attack inspired by these previous attack in this area. So as an example, let's imagine here we have a table of patient records here, right? And each row is encrypted separately. And the doctors wish to run an aggregation query to, let's say, count the number of patients for each disease type. Right? So how do we run this query normally, right? So let's say that you have a SQL, just plain SQL analytics system, and put that inside Enclave. What it might do is it might execute a hash-based aggregation algorithm, which each record is shuffled to a machine based on the disease type, right? And then aggregation is simply executed on each disease type. Yeah, pretty simple, straightforward. However, if it's hacker, right? Remember, the attacker could potentially have root access, right? Can observe page accesses, can observe network traffic pattern. Then he can observe that 4 records were shuffled to the first machine and 2 records were shuffled to the second machine, right? So, and armed with some prior public knowledge about the disease distribution, then the attacker can conclude that the first group, right, is most likely diabetes, and the second group is most likely cancer, right? And you can also backtrack the records to see exactly which patient record corresponds to cancer. Right? So in this case, the 3rd and 5th rows. Again, the only information he learns is about the actual disease type, so not about any other information. But let's say that now a patient comes in for a checkable treatment, and his patient record is retrieved via a filter query, right? Since this is just a plain regular filter, what happens is that the system will retrieve the 5th record, right? And now by kind of correlating this access pattern of this query with the access pattern of the previous aggregation query, then the attacker can learn information about, can kind of correlate this information together and learn that our patient Bob has cancer. Right, so the more queries you run, the more you can correlate. As you can see, this can result in a lot of information. So to solve this problem, we designed and built Opaque, which is an oblivious distributed analytics platform. And obliviousness here simply means that the access patterns, right, the computation's access patterns, are actually independent of the data content. And intuitively, what this means is that the access patterns shouldn't reveal information about the data content either. So the challenge here we're facing is again the fact that obliviousness is a very useful property to have, but it's rather expensive. And so in Opaque, we address the performance problem again via a combination of crypto and systems. And in terms of design, right, it's a whole stack of components. On the bottom is just ways of enforcing data encryption as well as computing verification, and the oblivious components are on the top, right? So the first oblivious component is new cryptographic algorithms that are used to construct distributed oblivious SQL operators, which then can be used to, you can combine them together to construct oblivious queries, right, out of these operators. And next, by using a systems approach, right, on top of this cryptographic algorithms, we actually designed novel database query planning techniques to further improve the performance of the query plans while still keeping the query's obliviousness property. So due to the time constraint, I'm actually going to only show you a small flavor of our query planning techniques. And I'll be happy to talk more about the system later on in the meetings, individual meetings, if you like. Okay, I'm going to show you, illustrate that technique using an example again. So here we have a sample SQL query that finds the number of patients in each disease group who are also over the age of 30, which roughly translates to this kind of oblivious query plan. So as you can see, we're just replacing filter aggregation using by our oblivious versions. So the question now we want to ask is, given this query plan, right, can we actually apply query optimization techniques to further optimize the performance while still preserving the plan's obliviousness? So if we take a look at how these operators are implemented, right? So they actually consist of more fine-grained building blocks, which we call opaque operators. So if you look at an oblivious filter, it actually consists of, it's actually split into 3 smaller operators. First is a projection, which projects each row to 0, 1 based on whether it should be filtered out. Next is an oblivious sort primitive, which sorts these rows by the 0, 1 column. And then finally filter, which filters out all of the 1 rows, right? And similarly, oblivious aggregation also consists of these 3 fine-grained operators. So our insight here is that from the current planning perspective, right, if we take a global view across the entire plan, right, then we can actually remove some of these opaque operators while still preserving the obliqueness. And so what happens, kind of transformation that we can do in this query is the following. So if we take a look at the Bog sequence, we first observe that the filter operation can actually be pushed up past the oblivious sort that follows it. And the filter push-up operation is a safe transformation that preserves the obliviousness. And here I would just want to contrast it with the kind of the normal rule that we see in plain text in databases, which is filter push down. And it's in fact, in this case, not oblivious, because if we were to push the filter past the first oblivious sort, then this filter operation will run first and the operator will leak which rows are filtered out. And of course, the data access patterns will no longer be independent of the underlying data. So what we have instead is a filter push-up operation. But then once we have pushed up the filter, then we can actually see that there are 2 oblivious sorts that are placed next to each other. One is a sort on the 0, 1 column, and the other one is a sort on the disease column, the aggregation column. And what we can do is simply do one multi-column sort on both of these columns together by merging the second one with the first one, right? So this is type of rule-based optimization. Whenever we see kind of this, whenever we see this pattern, we can always apply it. And with this, we have eliminated one oblivious sort, and which is the slowest opaque operator. And based on how selected the filter is, you could get up to 30% performance. So that is opaque, kind of went through it quickly. And previously I talked about Helen, which are just, 2 of the works that I did at the intersection of systems and cryptography. And really, being a system builder, one of my goals is to build artifacts that can be reused in the real world. And I have open source stuff for my projects. For example, Opaque was used by IBM Research for this volunteer matching application, and was also used by Alibaba and Ericsson internally. And recently I've been working on a pretty exciting project, a more umbrella project called MT Squared, under which there are some different sub-projects. Our system was used by Ericsson. You can see the blog post snippet here. We're collaborating with M Financial and actually collaborating also with Microsoft Azure Computational Computing, who has these hardware enclaves, as well as Scotiabank in an ongoing anti-money laundering effort. And so the plan is to actually go into production by the end of the year, not only with Scotiabank, but with hopefully at least 2 other Canadian banks for this real use case, which is very exciting. And again, I'd be happy to talk about that more later on. Okay. So with that, now I'd like to tell you a little bit more about my vision for the future of work, right? So I think that, this area of secure collaborative computation is still very exciting. There are many, many unanswered questions, especially if you want to, especially if my goal, right, is to build an end-to-end secure collaborative system for generic workloads. So it basically ideally has to satisfy these 3 properties, right? It should be able to handle the parties' incentives and constraints. It should be programmable, right? So that it can be run for any customized workload. And of course, we ideally want it to be fast. And right, and so from the kind of first direction, right, in terms of the incentives and constraints of the parties, what does that mean, right? So I previously mentioned, right, that Helen, the training protocol, focuses on only securing the training algorithm itself, but that is really only part of the picture. And the organizations that participate with each other often have complex economic relationships with each other. Sure, we can emulate a trusted third party using some fancy crypto, but a bank might not even be willing to commit to the computation, right? If it's concerned about things like, right, if it runs some kind of training, gets a model back, what if the global model only improves other parties' accuracies and not the bank's own accuracy, right? Where banks accuracy from its local model, right? What if the global model embeds too much information about the training data, right? And what if other parties are actually contributing garbage input into the system, right? Again, as I said before, even for MPC, you have to allow the parties to choose their own. So then, what is this example, right? This is really an example of the bigger problem of the tricky things around malicious inputs and leaky or undesirable outputs that could be produced in secure collaborative computation. And while MPC isn't the the straightforward solution, I think that it also has some interesting properties that one can leverage to address these issues, right? So, for example, MPC can be used to unrelease the result if necessary. You don't always have to release the final model as it is. And so what you can do is, put in some extra policy checks right before the model is released, and you can it can be different policies. You can release the model only if the accuracy exceeds a certain threshold, etc. Right? Another interesting extension is that it's also possible to release different results to different parties, right? So you can even, if there's an algorithm that you can construct that actually kind of releases different models to the different parties based on the quality of their inputs, that could be very interesting, right? So, of course, the question, right, the mechanisms are there, but the question still remains, right, how to correctly model each party's incentives constraints, right, both economic ones as well as privacy ones, how to design policies, right, to incentivize collaboration. Can we, from the crypto side, can we consider MPC with rational adversaries or even, all rational parties instead of at least one honest party? And finally, if you can't catch them, catch the misbehavior during runtime, right? Is there a way to make the parties accountable for their input if something goes wrong after the result has been released? Okay, so this is one interesting direction I want to explore. The second general interesting direction I would like to explore is what I like to call this democratizing secure collaborative computation. And what happens here is that, okay, so let's say that the banks are, we solve the incentives problem well, and the banks want to go ahead, right, with the secure collaborative computation. And what happens is that most likely they will designate some programmers to run this computation, and the programmer has limited to no expertise in advanced cryptography. So then they start exploring the space of, let's say, secure collaborative learning, and find that there are a bunch of works in this area. And you either have these hand-tuned protocols, like Helen, right? It's efficient, but it's a bit difficult to generalize if it doesn't exactly match your application, right? The kind of workload you want to run. And on the other hand, of course, you have generic protocols which can handle any kind of computation, but they're often slow, right? So the question I want to ask is, can we make these two directions converge? And more ambitiously, is there a way to actually build a system to automatically generate Helen, but for any custom workload, right? And I think that, while this is an ambitious goal and also leads to a much longer term vision, I think that, there are also some interesting questions to be answered here. So what I'm imagining is a system for automated generation of cryptographic protocols. It's a stack that, where at the top of the stack, where you have a domain-specific language that's exposed to the programmers, so that anybody can express their custom compute tasks using this high-level language. And then you have a compiler right in the middle that's able to compile, synthesize, and optimize secure protocol, cryptographic protocol, based on the using a variety of primitives and based on the workload setup of the parties. And finally, that can hopefully turn into a secure runtime execution that's automatically generated from the abstract protocol. So I think there are many interesting questions to be answered here from the crypto side, right? If you're designing, for example, if you're designing more kind of this a mixed protocol, right? Mixing different primitives together, how do you how do you construct, how do you efficiently and securely convert between these primitives, right? And from the system side, one of the interesting questions is scalability at a single party, right? Because as I mentioned before, right, these MPC frameworks, they are expensive, have to use a lot of memory. Can we use multiple machines or cluster to take advantage of that extra compute power? And finally, I think there are, with PL insights, I think it's possible to make the entire process not only automated, but provably secure, both at the protocol level as well as the implementation level. And so in general, right, I'm very excited to explore future directions within the area of collaborative computation. But I still want to, my ultimate goal is to build systems that really bring the capabilities of advanced cryptography to all users. And I hope that by bridging the gap between systems and crypto, I can continue to build secure, functional, and performance systems that not only make existing applications more secure, but also really enable new applications and opportunities that can benefit society. And yes, that is the end of my talk. Thank you. And I will take more questions if you have any. And right. I will, thank you. Maybe I'll stop sharing.
Thank you very much for the talk. So yeah, feel free to ask. We have time for a couple of questions. So feel free to raise your hand. Oh, I think I see Jennifer has another question. Sorry, I didn't see you right away because your name appears twice. Go ahead.
Okay, yeah.
Hi, I thought that was a really great talk. Thank you very much.
Thank you.
And the question I had was, so you talked at the end about maybe programmatically generating these kinds of like Helen systems. And when you were describing Helen, one of the things that you really talked about was, you were specifically looking at regularized linear regression. You had to apply kind of some, linear algebra tricks to get that to work. Do you imagine that you can, is your idea that you can programmatically find these linear algebra tricks, or would there still be some kind of intervention required by, the model expert or something?
Yeah, that's a great question. I think that the SVD insight, I do think that will be a little bit difficult to generalize. I have been, so one of the more lower hanging fruits is this combining different primitives together. So when you also, I guess I showed the zero knowledge proof plus MPC, we actually have a combination of homomorphic encryption plus MPC as well, which I didn't talk about that in the talk. For this automated, so I've been thinking of some. I would love to talk to the PL folks about it later. I've been thinking of whether it's possible to use something like super-optimization to find alternative representations of the program that are more possibly more crypto friendly. So that is one way to generate this. And if it's too hard, then maybe putting places where use annotations perhaps to help the programmers to identify what is taking so long, and then maybe they can come up with some domain-specific knowledge that helps the department.
Suyin?
Is the Helen system expandable to deep neural network? Because you describe a situation where you have a data set that has a lot more samples than the number of features. That's exactly the setting where people want to use a complex model rather than linear model. And also, neural network, each neuron is a generalized linear model. So I can see how it can be extended. And do you think, what would be your approach if you want to?
I will say this. I think neural networks are very interesting. I do not yet, I think training neural networks will be, very, very difficult inside MPC. I think it will take just a very long time. I think that on the other hand, I think neural network inference is actually a lot more doable. And there you have seen, I also have some work with some other students in the lab as well on convolutional neural network inference. And there you're really also seeing this pattern of mixing the protocols together, because neural networks, you have the linear parts rather than nonlinear parts. And so for the linear parts, there's some primitives that are good for that, and then for nonlinear parts, there's some other primitives that are good for the kinds of ReLU operations, right? So, and I think that can actually be, I'm pretty, optimistic about automatically generating cryptographic protocols for that. Yeah.
Okay.
So
Thank you.
That's definitely doable.
All right. I think we have a final question from Anna.
Okay.
Thanks for the great talk. I read Opaque a few years ago and really enjoyed it. Since then, however, we've heard a lot of problems with these hardware enclaves, especially the sort of speculative execution types of attacks. Going forward, is there anything that we can do at sort of the system software cryptography levels to fix that, or is that really just the hardware people need to fix it before you can sort of achieve the goals you set out?
Yeah, I mean, if the hardware people are, I know the companies as well, right, are willing to provide more isolation properties that make them side-channel free, then I think it will make the software folks like me, our jobs a lot easier. But of course, I think that even SGX, I guess you know, how SGX is a specific implementation, right? SGX as it is, I think there are some nice properties that it has. So for example, SGX, it has kind of two different stories, right? The side channels come from, the side channel attacks comes from the problems with the privacy side of the story, right? Whereas I think SGX has a much stronger integrity part of the story. And if that can be kind of hopefully more easily fixed, then that could actually be a great tool to combine, you know, SGX for crypto, because that's essentially one way to enforce a semi-honest attack. Yeah, so, and you know, these honest but curious protocols are simply a lot faster in performance. So yeah, that could be one way of dealing with the issue today, I guess. Yeah.
Thank you.
Okay.
All right. I think there are no more questions. I think the time is over. So thanks again for the talk. Feel free to unmute and clap your hands.
Okay, thank you.